Now here's where things start getting complicated. In this video, we're going to switch things up a little bit. In the past several videos, we've been using code that we've been building on video to video to video in order to sort of make a pseudo piece of robot code that does something in autonomous and you can drive around and teleop. In this video, we're going to talk about something a little bit more advanced. So I've cleaned up a little bit to make things a little bit easier to look at. In this video, we're going to be talking about PID loops. PID loops are a type of control loop that allow your robot to take in sensory information and do something specific with it. PID stands for proportional integral derivative. It has a lot to do with calculus and getting your robot to move based on information that it's been provided in a particular way. We won't get too much into how a PID loop works in this video. It's relatively complicated, especially if you don't have any calculus experience. But basically what you can think about it as is the P portion, the proportional portion, is reactivity. How violently do you want your robot to react to a difference between where you currently are and where you want to be? The I portion, the integral portion, basically takes in information about where you've been. It takes all of the information about how far you've already gone and where you currently are, and sort of tries to figure out what it needs to do next based on that. And then the D portion, the derivative portion, basically tries to figure out where you want to go next. It's basically sort of a future assumption. If you want to know more about how PID controllers work and more of the nitty-gritty of how all those pieces fit together, I do have some documentation that I can give to you that I have saved, that I use to learn about PID loops. But generally speaking, it's outside of the scope of this video, talking about how they work in particular. We are going to do a very high-level overview of how to set one up, and that's basically it. That being said, if you talk to some teams, you'll hear nothing but griping about how the PID control loop in the FRC libraries is garbage, and ignore it for now. It's good enough for our purposes, and if someone really wanted to rewrite it, more power to you. It's not anything that I even want to even remotely attempt, but apparently there are some teams who don't like the implementation of the PID control loop in the FRC libraries, and they write their own. But that being said, we're going to just use what's in the FRC libraries for this video. So if you've watched the previous videos, you should be fairly familiar with these things. Front left, front right, and rear right are our speed controllers, our motor controllers for each of the motors on our drivetrain, named for the side that they're on and the position that they're in. Speed controller groups, just the groupings of the motors from before, left side of the drivetrain, right side of the drivetrain. Differential drive drivetrain, basically just a singular representation of our robot's drivetrain so we can control everything as one piece. The Xbox controller object, just there so we can control our robot during teleoperated. And the ADXRS 450 gyroscope, that's the analog device's gyroscope that gives us an idea about the position of our robot. And then, of course, auto gyro facing angle is the position that we want to be in, the angular position where we want to be facing during autonomous. There is one thing that I've added, though, and that is this, private PID controller PID. This is how you create a PID controller in Java for the FRC. We'll see how we fill in all that information here in a minute, because it's actually a little bit complicated. But basically what this does is it sets us up with a way of turning our controller on and off and specifying values and input information for our controller. So what we see here is the general setup of all of our stuff that we need in order to get this to work. Now, if you notice, there is one thing that I didn't talk about in the gyro video. All gyroscopes have a calibrate method. Basically what that does is it takes different information from the gyroscope and sort of tries to figure out some tuning settings for the gyroscope in order to make the information come out a little bit more cleanly, a little bit more smoothly, and a little bit more accurately. Do not, under any circumstance, call gyro.calibrate anywhere other than robot init. You can probably get away with calling it an autonomous init, a teleop init, and disabled init once, but I really strongly advise against it. You should really be only calling reset in the init methods other than robot init, because depending on your gyroscope, the calibrate method can take anywhere from a few milliseconds to like 5 seconds. And that can delay your robot from starting in a particular mode, like autonomous, teleop, that sort of thing. This was actually an issue for the team where someone actually tried to help the team deal with a code issue, and they put gyro.calibrate in disabled periodic. And that was causing the robot to block for a few seconds during the beginning of a match where autonomous wouldn't start for 2 or 3 seconds while it was waiting for gyro.calibrate to finish. So keep that in mind. But basically all it does, at least where the ADRXS gyro is concerned, ADXRS, excuse me, is it asks the ADXRS gyro to calibrate itself. That gyroscope has onboard calibration capabilities. It has a temperature sensor that it reads to compensate for the ambient temperature of the air around it, so that way the readings are slightly more accurate than what it would be if it wasn't calibrated. For our previous example with the gyroscopes, I didn't call calibrate because it wasn't really necessary. If you start to notice weird issues, maybe do some tweaking. But that being said, let's move on. This part is where we get to set up our PID controller. There's a lot of stuff here. There's 5 pieces to initially set up a PID controller. A P value, an I value, a D value, a PID source, and a PID output. Now, the P, I, and D values we've already sort of talked about. These are basically just multipliers that take in information from your PID source, multiply those multipliers in, and then do some math in order to figure out what the output value should be. The way you figure out these values is usually by a lot of trial and error. And usually you won't use more than 2 of the values. Very, very rarely will you use all 3, at least as far as FRC is concerned. Normally you're going to have a fair amount of P, that's this value right here, this 0.061. You're probably going to have a very, very small amount of I, that's this 0.008. And you're more than likely going to have 0 D, which is that third value there. The reason for this is a little complicated. It goes into how PID controllers work. And some teams will use D over I, and some teams will use I over D. They can be used interchangeably for some things, but you still have to tune the values differently in order to get everything to work correctly. So, generally speaking, I just like to start with P and I. I find a nice value for P, and once I figure out what kind of tuning I need to do, I start to manipulate I a little bit to make everything sort of clean so that it doesn't bounce back and forth so bad. That being said, one thing that I do want to mention as a major disclaimer, do not work on tuning your PID if it is for your drivetrain in any area that is confined. Especially if there is a chance that your robot could take off like a shot, which is very, very likely with PID controllers. It's very time-consuming, tedious to tune a PID because you want your robot to react quickly, but you don't want it to react so quickly and so violently that it's constantly overshooting its goal and oscillating back and forth between, I want to be at 60, so I go to 80, and then I immediately go full speed backwards to 40, and then immediately full speed forwards back to 80. You want to make sure that you have plenty of room to work, because tuning a PID can be kind of complicated and dangerous if you're not careful. That being said, this example is for a gyroscope, so the robot is only going to rotate really fast if something goes wrong. But I also, just for safety reasons, and so I don't throw my 30-pound battery off of my robot, I do have the output divided by 2 down here, so that way the maximum speed is halved. You won't necessarily want to do something like that on your competition robot. You're going to want to try to tune everything to make sure that everything works correctly, but you can if you're having trouble with getting everything to work correctly. I did it this way because I was noticing issues when I was testing on a concrete floor. You probably won't have those same issues on a carpet, which is what the field normally has on it. That being said, the next thing that we have to set up is a PID source. A PID source is where you get the sensory information from in order to make your robot work correctly with your PID controller. There are 3 methods, 3 things you have to create in order to make a PID source. Set PID source type, get PID source type, and PID get. Set PID source type isn't useful in this example. A PID source type is either going to be K displacement or K rate. K displacement just means distance traveled, how far you've gone in a direction. K rate is how fast you're going. K rate might be used for something like whether or not your shooter is spinning fast enough. K displacement is used for something like this, where you're trying to travel a certain distance or rotate a certain amount of degrees, that sort of thing. The partner to that is get PID source type. In this case, the only thing that we do is we return K displacement. It's always going to be K displacement for us because all we're doing is using the gyro angle to determine what position we're at and how much further we need to travel, either forwards or backwards. That's basically all there is to a PID source. It's fairly straightforward, and normally your PID get method, like this here, is just going to be this. It's going to be returning one value. You can do more to make the PID source use different sensors and different inputs and different averages, but generally speaking, the most simplest PID source, its PID get method is going to look like this, where it's only returning one simple value, in this case, the angle. The last thing that you have to create for a PID controller is the PID output. There's only one thing that you need to specify, and that's the PID write method. It has a parameter called output that gives you a value between -1 and 1 to use with motors so that you can control them on your robot using the PID controller. In this case, what we do is we call on tank drive, and we set it up so that the left side is always moving forward, and the right side is always moving backwards at half of whatever the speed specified is. This just makes it so that when the PID specifies a negative value, it turns right. When the PID specifies a positive value, it turns to the left. Or left, right. I got those backwards. Left, right. Left, right. It's getting late. I've recorded, I don't know how many of these videos tonight. It's been like 2 hours. Anyways, that being said, that's all you have to do to set up a PID controller in general. In order to use it, there's a few more things you need to do, but there's a couple things we've got to see first. So in robot periodic, as I mentioned before, you can specify different things that have to happen all the time on your robot, regardless of what mode you're in, keeping in mind that you don't want them to take too long. In this case, what we do is we put the gyroscope raw value, that is the angle of the gyroscope, and information about the PID controller. When you put the PID controller on the smart dashboard, it shows things like your P, I, and D values, your current set point, which we'll talk about in a minute, and whether or not the controller is enabled or not. And you can actually manipulate those values in the smart dashboard if you want to do testing, so you can figure out what your values are supposed to be in order to make your PID controller work the way you want it to. So now we see some stuff that's very different. Our autonomous init, autonomous periodic, teleop init and disabled init methods are all different. And that's because there's not really a lot that you have to do in order to get the PID controller to start doing things for you. So the first thing we do is we reset the gyro. If you watch the gyro video, that just means that we set the rate of the gyro and the current distance, the current angle, to 0. The next thing we do is we reset the PID. Resetting the PID just resets all the background math. It makes sure that the PID is fresh and ready to start again from effectively 0. The next thing we do is we set the PID set point. The set point is whatever you want to do in the units you want to do it in for your PID controller. So in this case, you're basing this off of the units of the sensor that you're using as input. In this case, that's degrees. So what we specify our set point as is the number of degrees that we want to rotate the robot to while the PID is running. In this case, it's 90 degrees. So the set point defines where you want to go. If you were using encoders and you wanted to travel 60 inches, as in some of the previous videos, you would specify the set point as 60, so long as the value coming from your PID source was in inches. Your units have to be the same. The next thing that we see is PID.setAbsoluteTolerance. Basically what this says is how much wiggle room around the set point do you give. In this case, it's plus or minus 1 degrees is what I'm specifying. A well-tuned PID controller could probably get down to 1/4 of a degree with the ADXRS gyro. It might drift a little bit too much after a while, so you wouldn't want to wait too long. But generally speaking, 1 is a good number to be accurate enough to turn your robot, shoot, place something on a peg, drop something, what have you. Anything more sensitive than that, you may start running into other issues that we could talk about in another video, but in this instance, we're just using 1 degree of tolerance. Basically, we're creating a range of 89 degrees to 91 degrees that is acceptable for our PID controller in this instance. The last thing that we do in Autonomous Init is called PID.enable. What this does is in the background, it tells the PID to start doing its math in order to start telling whatever is in our PID output object up here that we created. It just starts sending information based on the sensor info that it's getting in from the PID source. Now, in Autonomous Periodic, all we do is make a smart dashboard call to this thing called PID.onTarget. OnTarget means that the set point has been reached within the tolerance specified. So it's that 89 degrees to 91 degrees range that I talked about before. Normally with OnTarget, what you would do is do your next part of your autonomous. So once you see that the robot is on target, you would immediately start something else, like starting something to make your robot put something on a peg, starting your shooter so that your robot is ready to shoot a frisbee or shoot a ball or shoot something else. In this instance, all we want to know is whether or not the robot makes it to the set point within the tolerance specified. And what this will do is it will put a little true-false value on the smart dashboard that says, yes, it is on target, true, or no, it is not. And that's basically it. That is our autonomous periodic. That's all that it does. You will see 2 other things here, both in teleop init and disabled init. PID.disable. This is always a good idea to do to make sure that should something go wrong with your robot, should something go haywire, should the mechanisms that are in place to make your robot stop moving when it is not in a mode that it is allowed to move in, this PID.disable is there to make sure that the PID loop stops sending information based on the sensor to the PID output object so that your motors stop moving, so that everything starts to spin down and that basically nobody gets hurt. And that's basically what that's for. I put it in both teleop in it and disabled in it because in a regular match, your robot is going to switch from autonomous to teleop, and so you want to make sure that your PID control loop actually stops before going into teleop. Otherwise, it will just keep going and you'll never be able to move. And I also put it in disabled in it just in case of that nightmare scenario that the robot decides to take off on its own even though it's been told to stop. At least calling PID.disable will make sure that the PID loop is stopped, hopefully, before it can do any damage to anybody. That being said, this video was a little bit longer than most. Obviously, this was a very, very fast rendition of something very, very complicated. If you have any questions, Facebook, email, text, phone, get a hold of me through a friend, whatever works. The next part of this video that you will see is a demonstration of the code that you've seen. In the next video, we will actually look at a rework of a piece of code that I helped write in 2013 for our frisbee shooting robot BP.